Thank you very much. Thank you for giving me the opportunity to speak here. So the main topic of my talk will be the study of the interplay between certain geometric structures and their automorphism group or group of symmetries. Of course, we have to focus on certain class of geometric structures. So I will mainly speak about conformal structures, either in the Riemannian framework or in the Pseudo-Riemannian one. So I first briefly recall what are the objects we will be studying. So the main object of study will be a manifold endowed with a Riemannian or a Pseudo-Riemannian metric. So I recall that a Pseudo-Riemannian metric of signature PQ is a smooth field of bilinear forms, non-degenerate, of signature PQ on the manifold. And we will be also interested, so I always do by convention, we assume that the number of minus is always at most the number of plus. When p equals to 0, we are in the classical setting of Riemannian geometry. When p equals to 1, we have what is called a Lorentz manifold. And we will be interested also in another structure, which is a little bit weaker, which is the conformal class of a given metric, namely all metrics obtained from one metric by multiplication by a smooth positive function on the manifold. So in the Riemannian framework, you see that the data of a conformal structure is just, you forget the distances and you still have the data of angles between curves that you draw on your manifold. Maybe it's worth saying what it's roughly the idea of a conformal structure in Lorentzian geometry. So if you have a Lorentz metric on a manifold, you get on each tangent space a null cone, right? So the Lorentz metric defines a distribution of null cones on your tangent bundle, like this. And the point is that all the metrics in a given conformal class have the same distribution of cones. So you forget the metric, you still keep track of the distribution of cones, and what you get is more or less a causal structure on your manifold. Namely, you have a notion of future directed vector, past, light-like, and space-like. So the notion of Lorentz conformal structure is more or less a causal structure on the manifold. For higher signatures, you still have, you can say that it's just a distribution of isotropic cones. But you won't have the notion of future and past. So those structures appear naturally at the, let's say, at infinity of pseudo-Riemannian metrics. So what you do generally is you have a non-compact pseudo-Riemannian manifold. You try to rescale the metric to make it compact. For instance, that's what we do with hyperbolic space. And what you get at infinity is a conformal structure. So two groups will interest us today. The isometry group of the structure, which comprises all smooth diffeomorphisms of the manifold preserving the metric. And the group of conformal transformations of the manifold, which comprises all smooth diffeomorphism, which preserves the conformal class. So it means that when you pull back the metric, you get another one in the conformal class. So what kind of general statements can we put on those groups? So the first general statement is that the isometry group is always a Lie transformation group. So in particular, it is finite dimensional. And its dimension is bounded actually by n plus 1 over 2 if n is a dimension of n. And the bound is tight and attained for the round sphere. So to have maybe an intuition why this group is finite dimensional. So it's rather more difficult to prove that it's a Lie group, but why is it finite dimensional? It's basically the fact that an isometry, either Riemannian or pseudo-Riemannian, is completely determined by its one jet at a point. It means that if you know the image of the point of a point by some isometry f and the differential of f at x, then you can recover f because the isometry must map geodesics to geodesics, and the differential tells you which geodesics goes to which one. So actually, you recover, at least locally around x, the map f if you know the image and the differential, thanks to geodesics. And by a connectedness argument, you recover f on the whole manifold. So what about now the conformal group? So here there is a gap between the dimension 2 case and the dimension at least 3 case. So if the dimension is at least 3, then the conformal group of a pseudo-Riemannian manifold is still a Lie transformation group. This time of dimension at most n plus 1, n plus 2 over 2, which will be attained as we will see for the standard conformal sphere. In the Riemannian setting, it's still true in dimension 2, but for, let's say, other reasons. But let me quote the following example of a Lorentz surface having a huge conformal group. We take a torus with coordinates, let's say, theta and phi, and we endo it with the conformal class of the Lorentz metric d theta d phi. So a conformal transformation here is a transformation which maps light cones to light cones. But light cones here are just a pair of isotropic lines. We are in dimension 2. And actually, the light-like direction corresponds to the factors. So each time you have an element in diff S1 cross diff S1, you get a conformal map for this structure. So you see that it's not finite dimensional. The situation is more rigid when the dimension is at least 3. And actually, you have the same picture as for isometries. A conformal map is entirely determined by its 2 jets at a point. And the proof is a little bit less easy, but the idea is the same. You have, in dimension at least 3, a family of curves called conformal geodesics, which is finite dimensional, preserved by the conformal transformations. And if 2 conformal transformations have the same 2 jets, they act in the same way on the conformal geodesics, and so they must be the same.
Why didn't they work in dimension 2 then?
Sorry?
Why didn't they work in dimension 2 then?
because you don't have this family of curves, distinguished family of curves, the conformal geodesic. To define them, you have to have what is called a Cartan connection, and this Cartan connection is only defined if you have this assumption on the dimension. So in dimension 3, conformal structures are called rigid geometric structures. In dimension 2, it's not the case. So now we know that both of those groups are Lie groups, and the basic question we ask is, given, let's say, a compact manifold, a compact pseudo-Riemannian manifold, what can we say about those Lie groups? Which Lie groups are allowed to be the isometry or the conformal group of a compact pseudo-Riemannian manifold? So the first case we are going to study is the Riemannian case, and it will be settled by a theorem called the Ferrand-Obata-Schoen theorem. So I now focus on the Riemannian signature. First of all, what can we say about the isometry group of a compact Riemannian manifold? So it's described by a theorem of Myers and Steenrod from 1939, which says that this isometry group, if the manifold is compact, is itself a compact Lie group. If Ng is a compact manifold, then the isometry group is itself compact. And the proof is rather easy. Actually, it's just Ascoli's theorem. Plus the fact that actually if you are a C0 isometry, meaning a transformation which preserves the distance defined by this metric, actually you are smooth. So if by Ascoli theorem, a sequence of isometries will converge to some C0 isometry, which actually is smooth by the regularity theorem. So that's a satisfactory description of the isometry group of a compact Riemannian manifold. Now, we would like to understand the conformal group. And for this purpose, the following notion is important and actually will be central in the talk. So this is the notion of essentiality of a conformal structure. What does it mean? It makes sense for any pseudo-Riemannian manifold. A pseudo-Riemannian manifold Mg is called essential when its conformal group does not preserve any metric in the conformal class. So in some sense, it's you have strictly more transformations than isometric transformations. So let me just make two examples. So a first non-example, an inessential structure, flat tori are not essential. for instance. So if you have such a tori with a flat metric G0, then actually the isometry group coincides with the conformal group. So the reason for that is that, so the tori is, let's say, obtained as Rn over Zn. Simplify. Any conformal transformation here comes from a conformal transformation of Euclidean space, which must normalize this lattice. But you can check that as soon as a conformal transformation has a non-trivial distortion here, it cannot normalize the lattice, because when you conjugate a translation, but such a transformation with non-trivial conformal factor, then it is shrunk to 0 after iterating, so it can't preserve a lattice. So any conformal transformation here comes actually from an Euclidean displacement on Rn. That's why the two groups coincide. On the other hand, you have a nice essential structure, the round sphere. And the reason for this is that its conformal group is a non-compact group. The conformal group of the sphere is the Möbius group, PO1 n plus 1, and it's non-compact. So by Myers-Steenrod theorem, it cannot be the isometry group, or contained in the isometry group of a Riemannian metric. So we have two examples. And before going further, I would like to give a lemma which characterizes essentiality in terms of non-compactness of the conformal group. So let me state this lemma. For a compact Riemannian manifold Mg, so excuse me, a compact Riemannian manifold Mg is essential, meaning its conformal group does not preserve any metric in the conformal class, if and only if it is non-compact. So we have a nice characterization of essentiality for compact Riemannian manifolds. The proof is easy. So we will see that inessential is equivalent to the compactness of the conformal group. So one direction is a direct consequence of Myers-Steenrod theorem. If you preserve a metric in the conformal class, then you will be compact. On the other hand, if K is a compact group acting conformally on a Riemannian manifold Mg, then you want to show that it preserves a metric in the conformal class. A way to do it is to pick any metric in the conformal class, so for instance G, and you make the mean under the action of K. So you build the metric G prime, which is the mean under the action of K of the pullback of G, and you integrate with respect to the R measure of your group. And by the very definition, so you get that K is included in the isometry group of G prime. Okay? So that's why we have this equivalence. So now I state what has been called Lichnerowicz conjecture in the Riemannian setting. So it is a question which was attributed actually at Andrei Lichnerowicz the 60s. So we said the round sphere is an essential conformal structure. You can build other essential structure by yourself. So we saw that flat tori are not a good idea. You can try other, and you won't manage actually. So this led Lichnerowicz to conjecture that, to ask, is the round sphere the only compact Riemannian manifold which is essential? Or an equivalent way of raising the question is to ask, is the round sphere the only compact Riemannian manifold with a non-compact conformal group? So the guess was right. There are no others. And
if you normalize the scalar curvature to be constant, maybe that's the way you got to study this. Is there a way of
I think it's a way Schoen did it, but I think it works only in the compact case. So sorry, because I will state a theorem including the non-compact framework. I think in the compact case there is a proof using.
that would be a natural way to pull out a specific Riemannian metric in the conformal class.
Yes, if you single out a nice Riemannian metric in the conformal class, you are done, and that more or less what Schoen did to prove the theorem. So what is the theorem? The theorem can be stated very simply. If Mg is a Riemannian manifold, which is essential, there are only two possibilities occur. Then either your Riemannian manifold is conformally diffeomorphic to the round sphere, or your Riemannian manifold is conformally diffeomorphic to Euclidean space. So the compact case of the theorem, which was actually the real question of Lichnerowicz, was proved in, so the compact case was proved in 71 independently by Jacqueline Ferrand and Morio Obata. Then there was a proof just after by Dmitry Alexevsky of the Hull statement, which actually had a serious gap, which was only discovered at the beginning of the 90s. So the general theorem, the complete theorem, was proved in 95 by Richard Schoen and independently again by Jacqueline Ferrand in 96.
I guess my question is, does he rely on the proof of the Yamabe? No.
Sorry?
You don't need the Yamabe,
No. So Schoen's proof uses this kind of ideas, but does not use the Yamabe solution, the solution to the conjecture. Actually, the proofs are made using an equivalent assumption. So this is a way to state the theorem. There is another way which involves more the dynamics of the conformal group, which is if I have a Riemannian manifold, the conformal group of which does not act properly, then I am either the round sphere conformally or Euclidean space. Okay, and to act properly means to be compact if the manifold is compact. So you recover. Okay. So now we are going to discuss what becomes Lichnerowicz equation in the Pseudo-Riemannian context.
Sorry.
Yes.
So the 71 proofs are actually okay in the compact case?
Yeah. And actually, Obata did proved something a little bit weaker. He proved that if the identity component of the conformal group is essential, then you are this. So, but the conformal group could be discrete and infinite, so it did not cover this case. So actually, this theorem in the compact case is due to Ferrand, and with a partial answer by Obata. And the general statement is so the both proofs are very different and almost simultaneous. Okay, so. So the question is, now if I replace, for instance, let Mg be a Riemannian manifold which is essential by let Mg be a Lorentzian manifold which is essential, and I put a compactness assumption, what can I say? Do I have the same kind of statement? Namely, there is a Lorentz compact object which is which has this property of being essential and which is the unique one to have this property. Okay. So to have a candidate for a statement in the Pseudo-Riemannian signature, I have to say who are the Pseudo-Riemannian analogues of the sphere.
I didn't get the first one of your lectures. Pseudo-Riemannian means signature N1 or any signature?
Pseudo-Riemannian means any signature, and in this talk, except Riemannian one. So, but you will see that the situation is rather different in Lorentz signature and in the full general signature. That's why I do sometimes. So Pseudo-Riemannian analogues of the conformal sphere. We look for the most symmetric objects in the Pseudo-Riemannian geometry from the conformal point of view. Most symmetric and compact. So those objects are described as follow. Those are the products SP cross SQ that you endow with the most natural conformal class of signature PQ you want to put on this product, namely minus the round metric on SP plus the round metric on SQ. Okay? And those spaces are called Einstein's universe of signature PQ. So let me explain why. So what is usually called Einstein's universe in Lorentz geometry is just the product R cross S3 with the metric minus dt square plus the round metric on S3. This is what is called Einstein static universe. And it was introduced as a cosmological model at the very early times of general relativity in 1917, I think. And so it turned out to be so, as here it is static. It means that it does not explain experimental data. such as redshift, for instance, and was soon discarded actually as a cosmological model. So, but from the mathematical point of view, those are this is a very nice space actually. This is the model space for all Lorentz conformal structures in the sense of Elie-Cartan, meaning that any Lorentz conformal structure is a structure infinitesimally modeled on this space, or S1 cross S3 if you want a compact one. So it's really a nice space that we don't want to discard. And
he always wrote that this was his biggest blunder.
yes, yes, because actually he had to modify the equation to make this space a solution.
And he missed the expanded universe.
So what are the properties of those Einstein spaces? So the main properties will be they are very symmetric. Their conformal group acts transitively on them and is a generalized Möbius group, OP plus 1, Q plus 1. And so other properties are actually they are the conformal compactification of Minkowski space of signature PQ. In particular, they are what is called conformally flat. And the most important for us will be that they are essential. So here I do the assumption P plus Q, excuse me, greater or equal to 3.
Is the group essential or the manifold?
Yeah, so that's the same. So the structure is essential, or sometimes we say the conformal group is essential. It's the same. It means that OP plus 1, Q plus 1 does not preserve any metric in the conformal class here. Actually, we will see that it does not preserve any metric at all. So here there is a little point that I have to stress. The situation is different from the Riemannian case because a wrong answer to show that this group is essential would be to say it's non-compact. So that's not a good argument. It's true, but it does not prove that it is essential because in pseudo-Riemannian geometry, you can have compact manifolds with already non-compact isometric groups. So I make just an example, which is interesting. So the example is the Lie group SL2R. It's a Lorentzian manifold. Actually, it is endowed with a B invariant Lorentz metric. How is it built? So
Did you know that it could be made into a weakly symmetric Riemannian manifold? It's the invention of Selberg.
what does it mean?
That it's the notion of weakly symmetric.
Yes.
You can switch points with an isometry.
Okay.
So Cartan's notion is you can invert your decimal
Yes.
point, which of course means you have transit. But he's just there's a non-trivial involution which switches points. His title of his famous paper,
Okay.
trace formula, is called On Weakly Symmetric Riemannian Spaces, and his main example of a weakly symmetric not symmetric
Is this one? Okay.
And
Okay.
Weakly symmetric at the moment. Doesn't seem to have caught up in France.
So how is this Lorentz metric built? On the Lie algebra of any Lie group, you have the killing form, right? It's a B-invariant symmetric bilinear form. And in the case of SL2R, it has a Lorentz signature. So you take this killing form, you push it by left translations. You get a Lorentz metric on SL2R, which is still right invariant by add invariance of the killing form. So the isometric group of SL2 with this metric is actually SL2R cross SL2R. Okay. And it turns out that it coincides with the conformal group. So now, what you can do is to take a co-compact lattice in SL2R. And the manifold SL2R over gamma is now endowed with a Lorentz metric, G0 bar, for which the left action of SL2R still acts isometrically. Okay, so you have a compact Lorentz manifold with SL2R acting isometrically, so a non-compact isometric group, and actually the conformal group is also SL2R acting on the left. So for here, conf M equals iso M equals SL2R. Okay, so we see that in the Pseudo-Riemannian framework, non-compactness is weaker than being essential. But one way to see that Einstein universes are essential is to say that PO, P plus 1, Q plus 1 does not preserve any volume form on Einstein's universe. So actually, hence is essential because if you have a pseudo-Riemannian metric on a manifold, it automatically defines a volume form. You have orthonormal frames, and you decide those frames have volume 1. So if you have a group like this one, so if you take a sequence tending to infinity in this group, what will happen on Einstein universe is that some open sets will be shrunk under the action of the sequence to closed sets with empty interiors. So you can't preserve any volume form here, and as a consequence, you can't preserve any pseudo-Riemannian metric. So you are more than essential.
So just a side, so SL2 over gamma, what are closed causal curves looking like?
Sorry?
Closed causal curves.
Causal curves? Yes, you. So on SL2R over gamma, so on SL2R, if you look at the right action of an elliptic subgroup, then you have yes, a closed time-like curve. So I think you have a lot on this quotient. So it's not. I don't. So anyway, on compact Lorentz manifold, you always have at least one closed causal curve. So it surely exists, but you can exhibit. You can describe them. I think.
Yeah, because they give something.
So causal. So.
No, causal means that it's causal.
So it's either time-like or.
What
Sorry?
What timeline?
Time-like.
Yeah, that's
So,
No, I just wondering
yeah.
if they give special elements in the pi 1. Anyway.
No, here, so, okay. No, but something that I didn't say is that, here, for instance, if you take at the diagonal, the left diagonal action, you see that the geodesic flow on the unit tangent bundle of a compact hyperbolic surface acts by isometries for some Lorentz metric. So that's an interesting example of a Lorentz dynamical system. So here I draw a picture in the Lorentz case. Some elements, for instance, of O2n have the following. Dynamics. So they have two fixed circles. So the dynamics look like the so-called north-south dynamic on the sphere, but you replace points or poles by circles. So those elements have attracting and repelling circles. And what they do, if you pick a compact set which avoids both circles, then if you iterate in the positive sense, this compact set will be shrunk to a segment on your attracting circle, and on the other direction, it is shrunk on a segment of your repelling circle.
What are we acting with? Some elements in the group?
Sorry?
Where's the dynamics? I haven't
On Einstein universe.
What's
The Lorentz Einstein universe.
Oh, the Einstein.
Yes, the historic Einstein universe, not the signature PQ. But in any signature, you have the same kind of picture, namely that some open sets are shrunk to. Okay. So now let me state a result about essential pseudo-Riemannian structures. So there are two parts, and the flavor of the theorem is that the situation is very different from the Ferrand-Obata theorem. So first, in the Lorentz setting, for any dimension and any integer g, at least one, there exists on so the product of S1 with g copies, with the connected sum of g copies of this product, infinitely Lorentz conformal structures which are essential. So what, if we compare with Ferrand-Obata theorem, so the difference is at two levels. At the global level, many topologies carries essential Lorentz conformal structures. And if you fix the topology, then you still have a non-trivial moduli space of such structures.
So I didn't understand what is
This stuff, it's you take g copies of this space and you do the connected sum, okay, and you make the product by S1. So it's not very relevant, I think, what is the topology of the manifold, but the thing we have to keep in mind is that a lot of topologies are allowed. As in the Riemannian case, only one topology was allowed, and on this manifold, only one structure was essential.
So this infinitely many distinct.
Yes, yes, of course. Pairwise,
Okay, so
pairwise inequivalent.
Yeah, all right. I'm not that great, but I want to know, are these discrete? Is there you say there's a moduli, is it a continuous?
No, it's not discrete.
So it forms a manifold, maybe?
It's hard to answer.
Is it form?
As we will see, the examples are built by Lorentz-Kleinian manifolds, mainly quotient of of open sets of this space by discrete groups. So there is some freedom to move the group and still be essential, but it's hard to understand what you can do exactly. And so the second point is that you can build structures like that which are not even Kleinian. So the holonomy is non-discrete, so it's hard to describe neatly what happens. But so all known examples are conformally flat, namely locally modeled on this space. So it's an open question to know if in Lorentz geometry, compact essential structures can only occur on conformally flat manifolds. We don't know. But as we will see, in higher signature, it can happen. So the second statement is that for any PQ satisfying this inequality, there exists on S1 cross SP plus Q minus 1, infinitely, again, pairwise disjoint, pairwise unequivalent, many essential conformal structures of signature PQ, which are not conformally flat. You can build examples such that the veil tensor is nowhere vanishing, actually. So here, even the local structure of the space is unclear, even with the essentiality assumption.
So okay, so show us the examples.
Sorry?
You will show us the examples.
Yes. So both statements are just building examples. So maybe I explain briefly how examples 1 are built. So since my time is running a little bit short, I just actually explain what you can do in dimension 3 in terms of hyperbolic geometry, because maybe it's more common. So to build examples 1 in dimension 3, what you can do is to begin with a hyperbolic surface. Obtained by a Schottky group on H2. So for instance, with 2 generators. But you can do it with more generators.
Infinite volume.
Yes, non-compact, that's the point. And infinite volume. Gamma 1 and gamma 2 generate a Schottky group. Actually, I could describe everything in terms of Schottky groups on this space, but maybe it's faster to go this way. A Schottky group of SL2R. I have to work with SL2R. Now, as we said, so the unit tangent bundle of sigma is just up to a double cover SL2R over gamma. Okay, it's endowed with a nice Lorentz metric, for which the geodesic flow acts isometrically, as we said. So it acts non-essentially. It preserves a Lorentz metric. So we look at the action of the geodesic flow phi t on this unit tangent bundle. So the point is that using those Schottky groups in Einstein universe, you can compactify all the picture. So this is, of course, a non-compact Lorentz manifold, but you have a conformal embedding of it into a compact Lorentz manifold. So there exists sigma, a conformal embedding of this Lorentz manifold into some manifold, which is actually S1 cross compact hyperbolic surface, but it's not important here. So this is compact Lorentz. This is conformal. And the point is that phi t extends conformally to ng. To ensure that I can conformally compactify this. Oh, there is no precise condition, but so the condition is that n is obtained as a quotient of some open set here, and it's my conformal compactification.
So I'm just trying to understand, what's the condition on gamma that's sufficient?
So the condition is that actually SL2R is an open, as a Lorentz manifold, is an open subset of Einstein 1, 2. Okay? So here you have a nice action. So this group acts on this open set. But actually, you can see it as a subgroup of O23, preserving the open set. And it acts, of course, so under this Schottky condition, it acts properly on SL2. So the point is that you can find a bigger open set in Einstein 2-3 so that the action is still proper. So you do the quotient, and it turns out to be compact. You do the quotient, you added something at infinity. Actually, you had tori here. And the point is that this flow still acts on the compactification as a conformal flow. Okay? And now, why is this flow essential? Because on this unit tangent bundle, the geodesic flow acts properly on big open sets. So there are open sets where every compact set is mapped to infinity under the action of the flow. If the flow extends here, it means that some open sets are shrunk to closed sets with empty interior under the action of the flow. So it cannot preserve any volume form, always the same argument, so it is essential. Okay, so by this process of compactification, you can build, so the final claim is that this manifold is essential. Okay. So this is a very peculiar example, but you can set everything in the realm of Einstein universe to the Schottky group here, to the Schottky groups of O2n, and make the construction directly on Einstein universe. So this looks as a negative result in the sense that
so if I move these circles,
yes, so yes, so you get different conformal structures. If you change the number of generators, you change the topology. Okay, but also you have examples here which do not come from such constructions. So you have more examples here. So maybe I just keep the statement here. So the statement says that being essential is not such uncommon in pseudo-Riemannian geometry. And that's because actually you can be essential and have a small conformal group. For instance, a single one-parameter group is sometimes enough to be essential. So I will just state rigidity results involving conditions on the conformal group, which says that this group is big from the algebraic point of view. So I will finish by those statements to show that sometimes you have analogs of Ferrand-Bata theorem in the pseudo-Riemannian setting. So let me set rigidity. Some rigidity results. So I go back to the first question. What can we say about the conformal group or isometry group of a compact pseudo-Riemannian manifold? And in the 80s, Robert Zimmer gave a lot of very significant results in this direction. So for instance, he proves the following. Let Mg be compact pseudo-Riemannian of signature PQ, and assume that connected simple and non-compact Lie group H acts on M. Then he proved if the action is isometric, then the Lie algebra of H embeds in OPQ, and in particular, the rank of H is at most P. And if the action is conformal, then you only have an information on the rank. Then the rank of H is at most P plus 1. Okay, so for instance, you get immediately that SL for R, for instance, does not act conformally on a compact Lorentz manifold. Because Zimmer's bound says that the rank must be at most 2. So here it's 3. It's 3. Okay. Now, what happens if the bound is attained? Then you have rigidity results. So this is, I will finish with this statement. It's a joint work with Uri Bader and Karin Melnik. So the statement first is an improvement of Zimmer's statement because it will deal with groups which are not simple. You don't make this assumption. So the statement is as follows: let Mg, as usual, a compact pseudo-Riemannian manifold of signature PQ. So if a Lie group, a connected Lie group, if a connected Lie group acts conformally on M, then, so first you still have the bound of Zimmer. The rank of H defined in a suitable way that I will precise just now is at most P plus 1. And most important, when the rank is attained, then your manifold is conformally diffeomorphic. So we would like to say to Einstein's universe, but it's not quite true. It's just the universal cover quotiented by a discrete group of conformal transformations. Actually, if you are not in the Lorentz situation, Einstein universe is simply connected, so gamma must be finite. And in the Lorentz situation, it's, you have more examples, but you can describe everything. Okay? So what is the rank of a Lie group? You just take the so you define it as the maximal dimension of an abelian subalgebra of H made of R-split elements. Okay? So this is an essentiality assumption, because if the action were isometric, we should have rank of H less than P plus 1. Okay, so but this is a stronger essentiality assumption because it involves algebraic properties of the group. And then you have a result reminding Ferrand-Bata theorem.
So H doesn't need to be a billion. So H could be a billion.
Yes, but it does not say anything. If it's abelian, the rank is 0.
What?
Yeah, you look at add H. Add H. So, okay. So then so it does not say anything for discrete groups, for instance. Too bad.
Yeah, so you might as well assume it's semi-simple. Yeah.
Right.
Because the rank won't change. Right? So if you just take the semi-simple part of your group.
Yes, but if the semi-simple part is trivial, for instance, if you take for group, I don't know, you take all, you take this group, this semi-direct product.
You're absolutely right. I mean, it gives more information in the first case.
Yes.
It tells you.
But you can have, for instance, a solvable group
Sure.
for which you can apply the theorem.
Yeah.
Just take, I don't know, all isometries of Rn and the translation, for instance. All homotheses of Rn, excuse me, and the translation. So as soon as you take n greater than 3, this group cannot act conformally on a Lorentz compact manifold, for instance. And still, the semi-simple part is trivial.
Yeah.
So it really adds cases which are not covered by Zimmer. Anyway, I think the most interesting part is this one, so the geometric part.
Thank you very much.